Those of you that read industry press and vendor announcement have probably seen an SDN acronym. Oh, okay. And the OpenFlow erupted a year ago or so, and there was hype like this will change the laws of physics. So all of a sudden, everyone will have equal access to every resource on the internet with no latency, like they invented tachyons or something. So of course, that's not true. There's a lot of hype with OpenFlow. And today I'll try to tell you what's real and what's hype and where it could be useful and where it totally doesn't make sense to use it. And you'll see that most of the vendors are focused on the use cases where it totally doesn't make sense to use it. So I've been in this industry for way too long. So I've seen things like, well, not as many things as Ron did. I started with DECnet, Index25, and IPX and AppleTalk and so on. And I've seen things like OpenFlow being proposed at least 3 times and failed like twice or 3 times so far. So I'm a bit skeptic. Or as someone said a while ago, if everything starts looking like ATM LAN emulation to you, you've probably been in this industry for too long. So last year, Greg Farrow did a great session of what OpenFlow is, so I will not bore you with those details. I'll just review the things so that we know what we're talking about. You know that in every networking device, you have, in principle, 3 different building blocks. The management plane, where you configure the device. The control plane, which is where all the smarts are. The routing protocols, the interaction with adjacent devices, topology discovery. So the control plane is the real brain of the box. It figures out what needs to be done. It figures out who is my left neighbor, who is my right neighbor, what prefixes they have, where do I want to send the traffic. And the result of this is the, in IP case, IP routing table, which is still sort of in the control plane. So this is the data structure that the routing protocols are playing with. And after we are done playing with that structure, it gets downloaded into the forwarding table, which is where the actual data forwarding happens. This is the data plane. And IP routing table is in almost all devices, in somewhere in software, in some RAM. And forwarding table could be in whatever weird binary tree data structures or TCAM or whatever it is. In OpenFlow, the idea is that you make the network devices totally dumb. So you actually rip out all the smarts. You remove the control plane. So what you're left is silicon that's totally dumb. It doesn't know what to do. It's fast, but it's dumb. So you have to fix that somehow. And you do that by introducing this controller here that will contain all the smarts. And of course, these devices have to connect to the controller first. And this is done over TCP session, running usually TLS or SSL, however you want to call it, so that these sessions are encrypted. Otherwise, that would be a great mechanism to break into the network and totally wreck it. And of course, people that are smart do this on an out-of-band control plane network. So there are people out there who are brave enough to do this in-band, and they will learn the hard way how interesting some bugs could be when you lose the control plane because you just cut yourself off. People who are smart are doing this over an out-of-band control plane network. And then the controller somehow builds the representation of the network in some data structure and does whatever a routing protocol would do, but it does this centrally. So for example, when you have a prefix here, the controller would figure out that the prefix is attached to this device here, compute the paths, and then download the forwarding entries into all the other devices. So it's like the whole network would be one single box. And of course, the proponents of this idea then say, and by the way, you don't need any routing protocols. Because, you know, the controller knows everything. There's no need for these devices to talk to each other. Yeah, sure. And how will you interact with the rest of the world? Oh, just use static routes. What about layer 2 connectivity? Yeah, static port channels work so well. Yeah, sure, until they break. So they really don't have a good answer to this. By the way, and Greg was talking about this last year, in OpenFlow you can match on almost anything. And that's the beauty of it. The protocol itself allows you to match on source destination port, layer 4 protocol, destination source IP, Ethernet type, VLAN, source and destination MAC addresses. And in theory, the protocol allows you to match on any combination of these fields, which of course is not implemented in any reasonably priced hardware. So the protocol allows you to do anything, and then you try to download that into an actual switch. And the switch says, no. And in some cases, oh, that's great, thank you. In some cases, we get to a situation, and I don't know whether HP managed to fix that, and I'm not picking on HP, it's just a nice example. When you use OpenFlow on HP switches, they do layer 3 forwarding in hardware and layer 2 forwarding on the main CPU, which is extremely fast, right? It's like tens or hundreds of times slower than doing it in hardware. And the reason they had to do this in the main CPU is because OpenFlow allows you to do forwarding based on source and destination MAC addresses. Have you ever seen a layer 2 switch that could do forwarding based on source MAC address? I haven't. And so there's this great protocol, and it's totally unimplementable in today's hardware at decent speeds. So in most cases, what you have to do is, if you want to write a controller, you have to write it so that it uses the features of the hardware you're using. And hardware from every vendor has different feature set. Because this came from an academic project, there is no capability negotiation. So you have no idea what the hardware is actually capable of doing. So you have to solve that in your own software. Yeah, that scales. So we are back to the situation where the controller vendors will have to do loads of interoperability testing with hardware vendors and have approved hardware list for this particular version of this particular controller. And by the way, that hardware has to have that software release because that was the only release we tested it with. So this will be a nightmare. Anyway, in principle, these things are great, so you can classify on anything, and then you can do header rewrites, so you could implement NAT, or you can push or pop all sorts of tags, or you can output to a port, or, this is good, you can send it to normal processing. So you could have a layer 2 or layer 3 switch that does whatever it does, and you just modify, let's say, an input echo with the OpenFlow, which is a great idea. This is actually one of the use cases I like, and no one is working on it. It's too simple, it's not sexy. These people were academics, so IPv6 headers, well, IPv6 only got into 1.2, and extension headers got into OpenFlow 1.3. And no one is implemented this in hardware. So what you get from the hardware vendors today is OpenFlow 1.0, potentially with vendor-specific extensions. Yet again, you know, we are back to that same game of vendor-specific extensions. And no one, as far as I know, has implemented OpenFlow 1.2 or 1.3 in actual switch. So you hear a lot of hype, and there's not much that you could actually do with these things. Anyway, just to give you an example how this controller builds the map of the network, this is how it actually works. So the switches connect to the controller, and so the controller starts building a network topology. OK, I see a switch, I see another switch, there's another switch, there's another switch. But the controller still doesn't know how they are connected. OK? So it can send a packet that says, well, tell me all about your interfaces. And so now the controller knows that this switch has two interfaces. It still doesn't know how they are connected to each other. So now what the controller can do is there is a mechanism to send a message through a port on a device. It's called packet out message. So the controller sends a packet out message, which is actually LLDP. Okay? And then this LLDP will be received by someone else, and this someone else would not know what to do with it. So it would send the LLDP packet, because it knows nothing about LLDP, back to the controller through packet in message. So this is how the controller can build the topology. Okay, now I know that these two switches are connected. Does anyone see a problem here? No. This works really great if you want to implement something like BFD, where you want to detect link failure in 2 milliseconds, and this is smaller than the latency to the controller and back. Fast feedback loops don't work well if you try to do them through a controller that runs over a TCP and SSL session. So there is no way that this network could react to real-time events in real time. Okay? The other problem is also that existing hardware has severe limitations in how many flow entries you can download into it. So right now you can download between 700 and 1,000 flow entries per second, which is okay if you have a small network and you only do topology changes. But some people are actually building controllers that use per flow entries, so every TCP session would be an entry. And I was talking with one of them, and he said, well, you know, and they have, by the way, Java-based controller. And he went like, this is not a problem, you know, with proper 4-core server and with the proper Java virtual machine from Sun, because it does the compilation, we got to 1 million flow setups per second. It's like, cool. How many of those were you able to download into the switches? Like 1,000? So this doesn't scale. The controller is not an issue here. The issue is the actual hardware, because there is always this very thin pipe between the CPU on the switch and the TCAM. And that thin pipe is the bottleneck in existing devices. Okay? So per flow setups, forget it. That doesn't work. And of course, then the OpenFlow proponents make claims like OpenFlow will replace existing routing protocols. And everyone loves to hate the routing protocols because they're loosely coupled, so you never know what will happen, and you have eventual consistency, so you never know that everyone has the same picture of the network. By the way, the internet as such doesn't converge anymore. We are not able to process all the changes in real time, ever. We are past that stage. So things are happening on the internet and it never converges because of eventual consistency. By the way, that's the only reason it scales. Because without eventual consistency, internet would never scale. Okay? And then the routing protocols are destination only. So everyone that wants to implement something like flow-based forwarding, like I want to send my backup traffic over some path and my production traffic over some other path, he hates this and implements loads of PBR, or policy-based routing, that we all love to hate. And this is not load aware, and so on and so on. So yeah, that's all true. So if anyone wants to start bashing routing protocols, this is your starter list. It's also true that they are reliable. They have been proven. They are deterministic. They are self-healing. They're autonomous, and they scale. So these are all the things that you have to reinvent with a controller-based architecture. So you must reinvent all the wheels. you must reinvent scalability, you must reinvent auto-discovery, you must reinvent fast conversions, you must reinvent control loops, you must reinvent BFD, for example. Because if the device is totally dumb and it cannot do BFD with the neighbor, you have to do it through the controller. And that doesn't work. So you have to reinvent everything, and on top of that, you have to provide some value or no one will buy the controller. Why did I put Google up there? Because they actually built an OpenFlow-based network. But what they did was they used that network to connect their data centers. So this is the back-end network that they use to exchange traffic between the data centers. It's not the production user-facing network. And what they have is they have a bunch of 10 gig switches in each data center at the edge, and they have OpenFlow controllers in redundant configuration controlling those switches. That makes perfect sense because the switches and the controllers are adjacent. They're very close to each other, and each controller only controls a few switches. And then what they do is they run ISIS and BGP between those controllers. So they actually reinvented the internet. Okay? Which makes perfect sense because on a small scale, you have the controller that controls like maybe 10 switches. And on large scale, you have ISIS and BGP. Okay, so what's new? The new thing is that they have a central traffic engineering calculation engine. And they download those things as paths into all the devices. So instead of running traffic engineering on every node and doing auto bandwidth and all the crazy things that we have to do with traffic engineering, they calculate everything centrally and push the paths to individual devices. And if that breaks, they're back to normal routing because ISIS and BGP won't break. So that's the perfect solution. But to implement that, they had to reinvent all the wheels. They actually decided to become a router manufacturer. And they can do it because they're Google. Okay? Now, for those of you that are old enough to remember frame relay or ATM or SDH, this is the same thing. We have an out-of-band control plane network with a central network management station called the controller that downloads forwarding entries into individual devices. And there is a reason no one is using ATM and frame relay anymore. But as RFC 1925 says, and you should really read that RFC if you haven't done that already, every old idea will be offered as a repackaged new idea, regardless whether it worked in the past or not. And there is ForSAS, which is exactly the same thing as OpenFlow, only based in IETF, not in the Open Networking Foundation. And there is MPLS-TP, which is more or less the same thing. The only difference between OpenFlow and MPLS-TP is that MPLS-TP can only establish label switch paths. Whereas with OpenFlow, you can also install fax forwarding equivalent classes on the ingress PE router. So OpenFlow can do a bit more than MPLS-TP. But the problems are always the same. If you don't do forwarding state abstraction, if you don't have paths or virtual circuits, it will never scale. And it's hard to have resilient network if you have centralized control plane. I mean, that's why internet was invented in the first place. And now we're going back to central control plane. Does that make sense? And there are the things I already mentioned. The important difference this time that actually might make it happen is that there is customer pressure. So there are a few very big service providers asking for OpenFlow. And in US, every academic RFP has OpenFlow as the checkbox. Do you support OpenFlow in your gear? No, you're out. That's why they're using Brocade switches for 100 gig links now. Because Brocade is the only company at the moment that I'm aware of that has OpenFlow on 100 gig links. Okay, so now you know what OpenFlow is. How are we doing time-wise? Okay, fine. So what is software-defined networking then? This is the original quote from Open Networking Foundation. The decoupled control and data plane, and because we have decoupled the control and data plane, we took away the control from the evil vendors, and now we will have heaven on earth. Well, not really, as you've seen. What vendors are doing is whatever they're shipping today, they call that SDN. There's so much SDN washing going out in this industry. Every API you have, you call it SDN today. And you'll see a few examples of what people call SDN in a later slide. And for startups, whatever will bring me VC funding, whatever I'm doing, it's SDN. I mean, there are two companies that I'm aware of that do load balancers. And they call that SDN because the load balancer has an API. Okay? And then there is a vendor that actually has an API on their box, and they have XMPP. So the boxes can chat with the operator. And it's a cool concept, but they call it SDN. And then there's this other vendor that has netconf, which is changing the configuration of the switches through XML over SSH. And they call that SDN. So whatever you have today, it's SDN, one way or the other. In reality, there are so many things that we don't do well. There are so many things that we could solve with SDN or OpenFlow or whatever you want to call it. But no one is focused on these things. So we do destination-only hop-by-hop layer 3 forwarding pretty well. And yet, everyone is focusing their controllers on this thing. Does that make sense? No. Layer 2 forwarding, we don't do that well, but there is Trill, there is SPB, there is Fabric Path, there is QFabric, there is VCS Fabric. There are vendors and standards solving this problem. And yet, there are OpenFlow controllers that solve this problem. Then, there's the optimal traffic engineering. And for those of you who are interested in complexity theories, traffic engineering, when you get down to it, is a knapsack problem. And that thing is MP complete. That thing cannot be solved in in polynomial time. So it's a hard problem. And solving a hard problem in a distributed architecture is really hard. That's why all MPLS-TE implementations suck in one way or the other. You simply cannot get an optimal solution if you don't have the full visibility of the whole network and all the requirements. And you never have that if you have distributed traffic engineering. So this is the problem that Google focused on. They solved the knapsack problem because they have a central database of requirements, and they do the central computation and download those things. By the way, what Google did is what people were doing with iOS 12.0 code 10 plus years ago. Only they couldn't use OpenFlow or API. They had to use expect scripts. But there were people, when Cisco implemented traffic engineering in, I think it was 12.0, it was called tag switching. At that time, people were computing paths around their networks and installing them as hop-by-hop traffic engineering tunnels in their routers. I know that some large either service providers or CDN vendors were doing that. And there is at least one vendor successfully selling an application that does that. So that's nothing new. What's sexy about Google's solution is that it has OpenFlow in there. And routing of elephant flows, we don't do that well. You want to push backup traffic over alternate paths because it's huge elephant flow, but it's only one TCP session versus thousands of TCP user sessions. And then there are things we don't do at all. Anything that has to do with policy. There is no good mechanism to push it out on demand. You remember the old applications when you had to install all the software on your PC before you could connect to a server? That's the stage where we are in the networking. You have to push things down to the individual networking devices if you want to implement new policies. Applications have moved along. Today, we have browser-based application where you download the new version of the application every time you connect to the website. And we can't do that in networking. And that would be a cool thing to solve. Imagine that every time a new device connects to your network, you authenticate it, you go into the database, you figure out what to do, and then you download the ECLs. And before someone tells me you can do that with 802.1x, just figure out how many clients don't support it. And some of those clients start with I. So you have a real problem if you tell that those clients can't connect to your network. And that's the problem University of Indiana is trying to solve with OpenFlow. And if they solve that, they will have a single solution that will work for all the clients, regardless of what the client supports. They will just have to write the plugins to authenticate individual clients. And it will work on wireline, on Ethernet, and on wireless. How is that for a cool application? And then, of course, policy-based routing can be easily done with OpenFlow. So you create a path across the network with MPLS forwarding entries. And then you install the classification entry in the first node, and you're done. And the security features, you can insert whatever you wish in the forwarding path, because with OpenFlow, you can push some traffic somewhere else into a different VLAN to a controller that would inspect it and send it back. So there are things that could really benefit from this. And yet, people are focusing on reinventing the wheel. Beats me. By the way, there are all sorts of things you can do if you want to combine the old with the new world. Some people that want to play with new protocols, they go with native OpenFlow. And then you have to reinvent everything that we did in the past. Or there's ships in the night approach, which is particularly popular with academics. So I have this running network at the university, and then some research guys come along and tell me that they want to run their research project on my network. And I tell them, no. So they go to the dean. And he puts pressure on me. So I give them a few ports and a few VLANs and make them into OpenFlow-enabled ports and VLANs, and they can play with that. So that's ships in the night. And the really interesting part is the integrated thing, which is what Juniper is doing with their SDK, where you can use OpenFlow as another input into the forwarding table or PBR table. So you have the traditional entries, and then you can augment them with OpenFlow. It's like downloading PBR configuration into your box. The nice trick here is that this is temporary. So you can do this without changing the device configuration, which is good because then tools like Rancid don't start jumping up and down that the configuration has changed. And it also is also interesting for troubleshooting, because all of a sudden you don't know what the authoritative state of the device is. If anyone has ever tried to troubleshoot DMVPN phase 3 networks, when the next hops are changing dynamically on demand, you know how much fun that is. And we'll have the same problem with OpenFlow. And by the way, here is a good example of what does make sense. Is it a year ago? A number of virtualization vendors figured out that, well, maybe we shouldn't rely on bridging. Hooray, after a decade they figured it out. So everyone is now offering some MAC over IP solution for implementing virtual networks. And if you're Cisco, it's VXLAN or VMware. If you are Microsoft, it's MVGRE. If you are open source world, it's GRE with Open vSwitch. And all these things work more or less in the same way. They take a layer 2 packet, they put it in IP, they send it to the other host. The real problem is, how do you know what the other host is? How do you know the MAC address of the other host? How do you build that layer 2 network? And this is what Nicira solved with OpenFlow. So they're using OpenFlow to push those entries into individual switches. Why does that work? Because it's totally decoupled from the core. They are an application running on top of IP transport. Okay? So they don't have to deal with all the problems I've mentioned before. They just rely on hosts having IP connectivity, and then they use IP connectivity to implement their virtual networking. And by the way, usually OpenFlow and SDN are mentioned in the same sentence. But that's not true. OpenFlow is not the only tool that you need to build an SDN solution, because OpenFlow is way too low for most people. It manipulates fib and TCAM entries. So OpenFlow as such is great if you're Google and you want to write your own router operating system. That's great. If you just want to tweak things a little bit, if you want to install an access list for this particularly troublesome user, if you want to push this backup traffic that other way, you don't want to write your own operating system, do you? Just imagine you'll have to write Linux every time you want to write a Perl script. You don't want that. So we need higher level tools. And there is something called netconf that has been lying around IETF for probably a decade or so. And what they managed to do in that decade is they can push device configuration in XML envelope through SSH session. And as of today, there are some drafts that would specify standard ways of configuring IP address on an interface or shutting down an interface, you know, the basic stuff. But they're still drafts and no one has implemented them yet. So today, netconf is just a mechanism that allows you to push existing routing configuration in XML envelope because XML is so cool. And in case of Juniper, that configuration information can actually be in XML format so that you could use some XML tools on the provisioning side to generate XML that would then be downloaded. And in case of Cisco iOS, it's actually CLI commands, apart from some newer solutions that can actually parse XML. And yet again, if you want to get something from the device, there is no standard way to do it. You execute a show command, and then you get the printout back as CData section in XML. And then you have to parse it yourself. So that's as far as netconf goes. The OpenFlow guys eventually, after a year or so, figured out that they need a configuration mechanism. So they decided to use OpenFlow config, which is netconf, and they have their own data model. Oh, by the way, this is another great story. When IETF started developing netconf, they were using XML. And XML has this validation language called XML schema, where you describe what a valid XML document for this particular problem is. And that wouldn't be good enough for IETF, so they had to invent a different language called Yang, which has the same use case as XML schema, but it's totally different. And I'm positive some people wrote a number of double column papers published in journals, so yeah, it made sense. And there's another one called Internet Routing System, which just might be the right level of abstraction for most of us, where you would be able to interact with the routing table. So with IRS would appear as yet another routing protocol, where you could insert routes or query the state of other routes. So this might actually make sense. And then there are the vendor APIs, and every vendor has a few of them, and more or less everyone calls that SDN. So Cisco has open networking, will have open networking environment. They have scripts in EM, or well, TCL or applets, and on Nexus OS they have Python scripting. And that Python scripting is so well done that you have to actually execute the show command and get the printout back in most cases. So there is not a real API where you could say, I want to change this parameter in OSPF. By the way, Juniper is no better, but in their case, it's in XML format, not in text format, but same functionality. And they couldn't rely on networking engineer understanding XSLT, which is another XML-based standard. So they had to reinvent that language, and they call it Slacks. It's actually XSLT in different syntax so that networking engineers are not confused by angle brackets. Delphorce 10 has Open Automation Framework, which is yet again Perl and Python. Arista EOS has Perl and Python. So any networking vendor that has Linux running on the box has Perl and Python. Well, that tells you a little bit. And F5 has iRules, which is more or less the only implementation of an API I've seen so far that runs in the data plane. Because with iRules, you can actually modify the behavior of the load balancer in the data plane. And here's a list of almost shipping products. So you can see that there are a lot of switches. There are 2 controllers that actually work, and this one that I don't know when they will ship, and 2 were announced. And there are a lot of open source things that you can play with. So it's an interesting concept, definitely. And if you want to try something new, now is the time to get involved. And remember that OpenFlow is a low-level tool. It's a tool. It's like a Swiss Army knife. It can do a lot of things, but it cannot build a rocket. Okay? You need other tools if you want to have a complete solution. Initial use cases that I see are large data centers and cloud providers, particularly with things like Nicira. And the most important part, today every controller vendor tells you how the OpenFlow will free you from dependence on hardware vendors. And they forget to tell you that then you will become dependent on their controller. Because there is no standard northbound API from the controller to the rest of the world. So you're just changing the lock-in. Choose your poison. More information, these are a number of websites, blog posts, and so on, where you can get more information. And Greg Farrow, that presented OpenFlow on last year's PLNOG, also did a webinar where he explained that into more details. It's available on my website. And by the way, this is a brief look into the SDN future. of the story, there will always be fat finger operators. And if you have more questions, just send them over to me, either email or Twitter, and I'll do my best to answer them.
Thank you. Any questions? Yes.
I have one question. At the very beginning, you said that the only reasonable implementation is to have auto network between controller and the network elements, which is good. That's what I understand. Mm-hmm. And if this is the case, so the question is how to control and build this network by another controller?
No. Well, actually, as you're coming from a certain company, I will use an example from that same company that I really love. It's like QFabric. In QFabric, you build the control plane network with traditional switches, and it's a layer 2 network that works in traditional way. And here is the same thing. The control plane network has to be an IP network, and it has to be controlled in traditional way. So you build a traditional IP network for the control plane network.
Oh, we need protocols.
Oh, absolutely. Oh, well, first you need to configure the IP addresses on the boxes, and any smart vendor would use DHCP for that. And then you need to connect the controller, and you need TCP and SSL for that. So yeah, absolutely, you need protocols. Yeah, well, as I said before, and maybe I wasn't clear enough, or well, I was imprecise. If you have an OpenFlow only solution where you actually control all the forwarding through OpenFlow, then the only sensible thing to do is to use an out-of-band control plane network. If you use OpenFlow in integrated mode, where OpenFlow just modifies something, then of course you would use an in-band network. For example, if you use OpenFlow to download access lists into wireless access points, you wouldn't have a separate control plane network for that, because the only thing you should not do, you should not touch the upstream link with OpenFlow.